All right, so here we are. We're doing N for AP and IBHL year two, where we're talking about vertical circles. The interesting thing about vertical circles is that we really can't say that we have uniform speed because the object, as it moves, technically, when it's at the top, and by the way, those of you watching me live are wondering why I'm moving my mouse. It's because later in the video, there's a little circle there. But at the top, we know that it's actually, for a moment, going at a uniform speed. On the way down, it's speeding up. So technically, we cannot use any of these equations on the way down. We can't use any of the equations on the way up. So you'll notice that on every single AP or IB question related to this, it'll only be at the top or it'll be at the bottom. Because at those two places, just for a moment, we can say that we have uniform speed. So let's go ahead and start doing this problem. We have a ball that has a mass of half of a kilogram. We have a radius that's given as 0.75 centimeters. And we've been told that the tension at the top, and notice at the top the tension is pulling downward. At the top we have a tension of 4 newtons. So the first thing we want to do is sort of draw a little vector picture that helps us understand that. And then what we're going to do is add our two vectors. So we have a downward vector due to tension, which is 4 newtons, right? We also have a downward force vector of 5 newtons that's due to gravity. And so the net force acting on the object when it's at the top, that net force is known to be 9. And that's because both of those are acting downward. And so we're just going to say 5 newtons plus 4 newtons. And we've got 5 newtons. We've got 9 newtons total going downward. So the net force when you're going in a circle is providing the centripetal force. So we set this equal to Fc. And that means that we have an equation for it, which is mv squared over r, where v squared over r is the centripetal acceleration, and we multiply by the mass to get the centripetal force. That centripetal force is 9, so all we need to do here is set up an equation where we plug in a 9, we put in the mass, we solve for v. From that, we'll get a velocity at the top, which was, I'm sorry, someone tell me that? 3.67 meters per second. So we have 3.67 meters per second is the velocity at the top. So what that means is that we are happily done with number 1. Okay? Number 2 asks us for the velocity at the bottom of the circle. And so at the bottom of the circle, from the top of the circle, we're going to have to use conservation of energy. So the total energy at the top equals the total energy at the bottom. So we've got PE plus KE at the top equal to PE plus KE at the bottom. And it's pretty straightforward. You guys, to plug this in. So at the top, be careful, the MGH at the top is not just the radius. Because we have a radius that's known to be 0.75, means that actually the difference here is 2 radii or a diameter. So we're going to need to use 1.5 for the height there. Okay? That's plus the 1/2 mv squared at the top. So this is all at the top. At the bottom, we have no potential energy. So we're going to set that equal to 1/2 mv squared at the bottom. And we expect to see a higher velocity. We can cancel masses if we want, or we can calculate it all. Anyway, we get a velocity at the bottom. Anybody want to say what the velocity? 6.6. Has that been verified by anybody? 5.48. Oh gosh, did we use 9.8 or did we use 10? Okay, so we're not agreeing on the velocity at the bottom. That's unfortunate because now this video is trash. Ruin the video anyway. Okay, so anyway, I guess I don't know what to do with this video at this point. So I guess it's for Jose. So the video is only going to be for Jose, so we can not worry about it quite so much. So can we figure out the velocity at the bottom? Seriously, we don't know what that is. So here, you know what I'm. We're ready to go. So it's 6.6. Okay. Well, my software supposedly I can take part of a video and just like delete it. So I'm going to try to do that afterwards. And if I can do that, we can pick right up where we're at right now on the video. So I'm going to pretend that everybody agreed that 6.6 was the right answer, and I'm going to move on in the video. We ready? Okay. Ready, set, go. So now we know that the velocity at the bottom is 6.6 meters per second by using the conservation of energy. What's interesting is that the tension at the bottom is going to be very different. And the reason for that is when we're at the bottom of the circle, tension's pulling up, but gravity's pulling down. And so the net force when we write it, which is the centripetal force, is actually the combination of the tension, which is the force of tension, minus, right, the normal force, which is the force of gravity. And so what that means is that the tension, or if it was a loop-to-loop problem with cars, it'd be the normal force, but we're going to say tension here since it's a rope that's pulling up on it, is going to be mv squared over r plus mg. And this is at the bottom what we're going to need to do. So take a second and see what you get for the force of tension there. Anybody have that yet? For sure. What's the centripetal force? Around 29 newtons. And then for the gravity, we still have this 0.5, so we still have 5 newtons. So the overall tension is going to be 34 newtons, right? And that is the answer to the tension at the bottom of the circle. And so at this point, we're happy with all three, and we can stop this fantastic video for the people that weren't here to listen to it, okay?